We have another session.
Already done.
We start. Good afternoon, everyone. We are absolutely delighted and so excited to be here with all of you to discuss this very new generation issue and a challenge that's confronting us and worrying us at the same time. And to put it simply, the simple question that we have in front of us today is, how do we urbanize? How do we build frenetically our houses, our offices, our retail centers, the whole frenetic construction, the built environment that is shaping up now in all our cities and towns and across the region? That how that growth needs to happen in a climate challenged world, when the whole livability is getting hugely impacted by climate change, then how the built environment needs to respond to that to make ourselves, our built environment livable, that we are able to take care of the well-being and larger sustainability of the new growth. Now, it's from that perspective that we have planned this very interesting session today. And we have with you the leading experts, and just experts, they are the practitioners who have actually demonstrated that how innovative practices can take shape and that can become part of the reality to make livability sustainable, to make our built environment sustainable. So before we go deeper into the session, let me introduce you that who are we today here. I'm Anumita Roy Chaudhary and working on sustainable cities from Center for Science and Environment. With me, I have my colleague Rajneesh Sareen, who is heading our program on Sustainable Habitat and Building Program. My colleague who's Sugir Grover, who is looking deeply into the issues of sustainability in built environment. And with us, we have a very exemplary panel of experts with us and who are also the practitioners and leading the debate in the country today. So we have with us Dr. Jyotirmoy Mathur, who is the professor in Malviya National Institute of Technology in Jaipur. We have Mr. Ashok Singh, Chief Operating Officer, NIIT University in Indiana, Mr. Mahesh Vasuvanna, Founder and Director, MCD Berry, and Mr. Neeraj Manchanda, Managing Partner, Neeraj Manchanda and Architects. And we have Mr. Gajanan Ram, Vice President, Council of Architecture. So you can imagine that how exciting and informative and insightful the session is going to be. So without wasting any more time, let's go deep into the conversation. Let me just flag off some of the context of the whole conversation as it is evolving today. Just share our screen. And just to put the whole conversation into context of what is happening today and why are we discussing this, we just thought that we will first share with you some of the key emerging challenges which is going to shape this conversation in the coming years in India. So clearly, as I just said, that what we are most worried about is the changing climatic pattern, and we know that it is going to change phenomenally in the coming years. The studies that we have carried out recently, and as you have also heard and read in the media and otherwise, that how difficult living is going to become as the world is experiencing some of the record-breaking temperatures now. And this time particularly, it had become quite sensational when it was reported that July this year was one of the hottest month globally. And today, World Meteorological Organization is actually predicting that it's going to get hotter and worse And this means, and what does this mean actually? So if it's warming up, it's hotting up, then essentially this means it's going to increase our cooling demand just to say stay comfortable. And what technically today the experts tell us that to be thermally comfortable. But how do we ensure that? Because if we don't, then it is going to increase our dependence on active cooling when all of us are going to just try and buy whoever who can to buy and switch on their air conditioners. And as you know, that more and more we depend on active cooling, we are going to increase energy guzzling. The numbers are actually quite scary that the energy demand that is going to get catalyzed because our dependence on active cooling is huge and humongous. In fact, the estimates available from NITI Aayog is telling us clearly that 65% of the energy demand in our buildings that comes only from space cooling, whether you're in a residential building or a commercial building. That's huge. And then what is worrying about the fact that if we do not intervene right now to modify the built environment with the right approach to architectural design, with all the other available innovative approaches that are available to us that we will be discussing today, then we are going to be in deep trouble. But what is also interesting that there is a policy response to this challenge today. As you know, that India now has a cooling action plan, and that cooling action plan, which has laid out the target and also saying that we now need to actually reduce the demand for cooling so that, we can actually limit it by about 25%. And the reduction in cooling energy requirements, and there are dates given that we should be able to reduce the cooling energy requirements by about 35% by 2038. What is important to recognize in this target setting is that there's a huge emphasis on that we need to reduce the non-refrigerant, we need non-refrigerant based cooling and not the technology-based, refrigerant-based cooling that, as we all know, is the air conditioner. Essentially, what we are talking about is there a way for sustainable cooling? And what is that paradigm of sustainable cooling that will ensure thermal comfort for all? That is the goal that the India Cooling Action Plan has set for us. Now, if we do not address this, as Ministry of Environment, Forest and Climate Change has predicted, that the cooling demand in buildings can grow 11-fold in the time frame of 2037 and 38. And the space cooling is going to increase from 1 AC, but the demand, in fact, the prevalence of it will be from 1 AC per 100 persons in 2015 to 15 ACs per 100 persons by 2047. That's the NITI Aayog's data. Now, if that's what is going to happen, then just imagine the kind of energy demand that is going to create and how that is going to upset not only the household energy budget, but also the national energy budget. And we are talking about this challenge when around 2017 and 16, about 8% of the households actually had air conditioners. But with growing income and urbanization, that this trend is just going to explode in the future. So, in fact, the anticipated rise is expected to be about 40%. Now, what we really need to keep in mind that it's just not about the building, but when you are linking the current urban growth with climate change, what we also have to keep in mind that what are the different contributory factors to this phenomenon. One is that our cities more populated and we are getting more dense cities. And as a result of that, the result of that invasion of concrete, the green and the blue is disappearing very rapidly from our cities because we have not been able to integrate that sensibly. And in addition to that, there's a huge heat generation. that is happening in our cities because of the waste heat from our vehicles, from the air conditioners, and the concretes trapping heat. So all of that together is increasing the heat effect in our cities. So not only the overall ambient temperature rising, but within the city itself, we are beginning to see this kind of heat trap being created. And it is predicted by 2100, cities across the world would warm up by as much as 4 degrees, and cities are going to be much warmer than their surroundings. So how that is going to impact the thermal comfort expectations of the people and the choices that they're going to make. This is one data crunching that we have done, and we always love to show this. This is for Delhi, and it is showing that how during summer, the energy, the electricity consumption is correlated with the heat index in the city. And what you will find that till the time that if you can see that two vertical bars, that between 20 to 30 max 32 degree temperature, that around that heat index, that you see that the electricity demand is quite even. But the moment we cross that bar and we exceed 30 or 32, then you just see that sudden spiraling of the electricity demand. And that clearly is showing, and that's an impact of the cooling demand. That's when we are all switching on our ACs. Now, this means that if our buildings are not thermally comfortable, then the reduction that we would want to desire for ourselves in the temperature, in the internal temperature by using AC, it can actually be just to reduce the temperature by 5 to 7 degrees centigrade or even more from what you are being exposed to. You are certainly going to be using a lot more AC. But the upshot of the whole argument is that, and if you look at this, the range of temperature given by the BIS for the adaptive thermal comfort, and if you go by the cities, and here we have earmarked some of the cities where you find that you do have that level of 30 degree, around that, which we then try to cool it further by applying air conditioners. Essentially, the point that we are trying to make is that if we have to increase the time of the way we can stay comfortable without using AC, that how can we reduce the air-conditioned hours by intervening with our architectural design and technical approaches? That's where we really want to take this conversation to. And that's the opportunity for us, but that opportunity which is going to get limited and constrained because of the way the heat island effects is increasing in our city. So if you see here that, and this is a very exciting mapping that has been done by our team, where we have looked at these different cities and we are showing that how land surface temperature in these cities have increased over time between 2014 and 2022. And you can see that on an average, you're really talking about the increase between more than 2 degrees to more than 5 degrees centigrade. Therefore, what happens, and it's the further mapping that has been done based on that, where we've actually tried to identify the urban heat centers. And urban heat centers where for over a period of time, the given pocket of the city where the temperature has actually, the land surface temperature has actually increased by more than 45 degrees. And clearly, as you can see here, Jaipur, Delhi, and Pune being the worst, and it's clearly showing up in the map. And you do have, but Kolkata is comparatively better. So clearly, you can understand the relationship between this changing landscape in the city where we live and where we are going to build and where our houses are and what it means for our thermal comfort. So keeping this some broad concerns in mind, what we want to debate today, that where should we go and how do we address this challenge? And clearly what we have done, and you will be happy to see that this, maybe if I can show you that this very interesting compendium that we have compiled based on the actual architectural interventions and the innovations that the progressive planners and architects have done in different buildings, in different campuses, in different parts of the world. And this documentation has really helped us to understand that how it is possible to change the practice. And therefore, learning from those experiences, we have to address the roadmap for the future. And it's very clear that in that roadmap, we need to be contextual. We need to find climate-sensitive cooling solutions that are sustainable in the given region, where it is just not about one building, but we really need to take a system approach that the site and the area level planning that becomes critical to enhance the microclimate, to include vegetation, water features, permeability, clustering, layout, everything that influences the built environment and the buildings around. And then to look specifically into the built form, the buildings themselves, and leverage their microclimatic advantages to improve adaptive thermal comfort. And to do that, we need to enhance the link between buildings and the open spaces, use daylight, ventilation, natural ventilation sensibly, effectively, utilize the courtyard effect, and all the different architectural passive designs make that innovation possible. Be very careful about the building envelope and material, understand the interplay of materials, shading devices, insulation, reflective surfaces, but everything that helps to address the heat gain in the building. And then once we have with all of these, able to reduce the overall thermal load on the built structure, then look very sensibly, rationally, scientifically, that what are the active cooling methods that are possible, that we can adopt, which are less energy consuming and can be used flexibly, variably, and reduce the requirement of air conditioned times. So, and do that very efficiently. So that's where the challenge is. So clearly, therefore, keeping in this context in mind, we want to take this conversation forward. And to take this conversation forward, I would like to invite my colleague, Sugit Grover, who has worked on this compendium, looked into the specific cases, and he will take us through what are the learnings, what deep dive documentation we have done, what has been our learning so far that can be integrated with the roadmap going forward. Sugit.
Thank you, Amitaji. So the way out, well, to be honest, a lot of the way out actually comes very much from India's traditional design sense that has been evolved since centuries. Indian traditional architecture as such recognizes that the buildings need to respond to the native climate and geography in various aspects, let's say site planning, building form, envelope, materials, opening sizes, even to vegetation, what kind of a vegetation should one be using. They are all tweaked in response to the local context to achieve this bioclimatic design. And as a result, India's per capita space cooling energy consumption is as low as 69 kilowatt hour, which is about 1/4 of what is prevalent in the global scenario. Now, how has the market actually responded to all of this, energy surge that is expected? There is a one-stop solution, which basically means there is a HVAC, there is an air conditioner that is being used as a one-stop solution to reach comfort zone. While we understand that there can be many more. In fact, we say that a building needs to enhance its microclimate, have appropriate building form, have envelope and a material specific to the context, and then use an apt cooling technology. And only then one should be using some sort of cooling system. We call all of this the cooling web, and all buildings should be going through this before actually using HVAC refrigerant-based cooling system. Now, CSC's previous research on this subject has taught us that basically a building sort of loses its advantage in a badly designed site plan. So once you put a building, even if it's oriented correctly, if you lose if you put it in actual site context, it completely loses its meaning, and all sun, wind, microclimate, all of these factors actually go for a toss. We also understand that our codes have been a little weak at regulating urban forms at area scale. For example, at city scale, you might have Town and Country Planning Act, might have master plan, you might have on building scale, you might have the National Building Code, Energy Conservation Building Code, various building bylaws. But when it comes to area scale, there is not much that is actually happening. So in our publication, the Cooling Web, you will actually find all of the case studies have all of these systems embedded into them. We have passive measures applied as well as the active cooling technologies applied. In the passive measures, we have multiple components inside them as well, which we'll explain. So if I talk about, let's say, microclimate enhancement, we see good examples of external shading coming up in IIT Gandhinagar, vertical plantation happening in IIPH Gandhinagar, permeable surfaces as well as plantation, extensive plantation done in NIT Nimrana. When it comes to building form itself, we see a lot of the buildings were actually across the case studies were oriented either north or south. This is an example of IIIT Delhi. NIT Nimrana uses a courtyard sort of a structure, and many of these buildings have been placed in a way that they're able to mutually shade each other, which again has some benefits in terms of heat not getting in. When we come to envelope and materials, window shading is something very important, and we see wonderful examples coming in from IIIT Delhi as well as IIPH Gandhinagar. IIPH Gandhinagar, in fact, has embedded its shading devices along with a vertical gardening system, which again reduces the amount of heat that's actually getting into the facade. A cool roof system has been designed in IIT Gandhinagar. And you would also see a double facade system in Gujarat Vidyapeeth Ahmedabad. You would be able to find more examples such as these in the Cooling Web booklet as well. When it comes to active cooling, this is where things even get more interesting. We have divided the solutions into two categories, low impact cooling as well as refrigerant-based cooling. And then consequently, they also have a relationship with renewable sources, and you will see how that happens. So let's break down what the conventional HVAC system, really the one-stop solution that we usually have in our buildings. What do they actually do? They achieve cooling. We saw examples of earth-air tunnel doing that. They achieve ventilation. We saw wind towers being used in various buildings in our case studies. And the HVAC system also dehumidifies. This is a little less prevalent, but we also see examples such as coming up in Nalanda University of such a system. And all of these case studies have also taken all of these into account. Let me start off with the Indian Institute of Technology in Gandhinagar, which uses a passive downdraft system. I will not speak too much about it because Mr. Neeraj Manchandra will be taking this case study in more details. We have Gujarat Vidyapeeth Sabharkand building in Ahmedabad. What it does is there is a water sprinkling mechanism. Firstly, there is a well. There are wells which are placed close to the building. There is a water sprinkling mechanism inside the well. So what you'd see is evaporation happening there and cooling the air. This air then actually travels through an earth-air tunnel and enters the building. The earth-air tunnel in itself, the earth-air tunnel is kept 4 meters below the ground, so it acts as a heat sink, and some of the heat actually gets absorbed by the earth itself, and then it enters the building. This is an image of the building in itself. Once that happens, so this is where we start our story from. There is the well, it is covered and shaded very nicely. And this is where the fans are kept, which are helping in the evaporative cooling. The air then travels and enters inside the Sabharkand building itself. We have Indraprasth Institute of Information Technology in Delhi, which is a wonderful case study for passive design, as well as a good district cooling system that they have used in our system. And then comes the NIT University in Nimrana. What it does is that there is an earth-air system involved. There are wind towers that catch the wind, they filter the wind, and then there is a tunnel that is again kept below 4 meters inside the ground. The air travels about 100 meters inside this, and then it is made to enter the spaces. This is what the wind towers look like. This is what the tunnel looks like. This is about 100 meters in length. And this is what what is the device that actually makes the wind enter, the cooler wind enter inside the spaces, inside the spaces that have to be air conditioned. This is the entry points into spaces. This is an image of the classroom, and this is the exit points for air. And these are the shafts because of which this heated air now, the cooled air that has become heated due to humans or equipments inside the spaces now, this is from where it starts exiting. In the end, we have Anil Agarwal Environment Training Institute, but we'll come back to this case study a little later.
Thank you so much, Sudhir, for giving this very interesting snapshot of the innovation and practices. Now, against this backdrop, we would now like to start our panel discussion, and I would like to invite Dr. Jyotirmoy, if you can now share, and the whole, as I was saying earlier, that the whole focus of this conversation today is the scope and the depth of sustainable solution, the cooling solution, but also the scalability of this solution so that we can really influence the future built environment. So Jyotirmoy, it would be great to hear from you, your thoughts.
Thank you, Dr. Anumita, and wonderful background that both of you have said. So let me, is my slide visible?
Yes, you can see it.
Okay, good. So I'm going to speak about basically three things. One is, of course, the earth air tunnel, example of which has been shown by Sudhir, but I'll touch upon a little more technicalities of how to design a good earth air tunnel. So evaporative cooling is the next topic which has been given to me, but I have extended this to a relatively new topic, which is radiant cooling. But again, I'll try to show the pathway for integrating the previous two topics, that is earth air tunnel and evaporative cooling with that. A little bit of my background. I am Dean of Academic Affairs at NIT Jaipur and basically a professor in mechanical engineering. And we have a Center for Energy Environment where these experimental facilities are there. Earth air tunnel, 60-meter long earth air tunnel on which we keep doing a lot of experiments. Evaporative cooling, different kinds of evaporative cooling systems and radiant. So all the three systems I'm talking about, it's basically dependent upon the findings that we had through various master's and PhD theses that my students had, and of course, some of the projects that we helped deploying these things. So earth air tunnel, basically the concept comes because of a wonderful property that Earth offers us, that it is a practically infinite source or sink of heat, whatever you treat us as. If your ambient is cooler, then, so if you go deeper into the ground, roughly 4 meters, most of the fluctuations that you see in ambient air temperature, they flatten out because of the thermal resistance that is offered by the earth. Of course, it depends upon the nature of soil, but yes, practically at 4 meters, it is constant. And if your ambient is cooler than this, you can use it for heating air. And if your ambient is warmer than this temperature, you can use it for cooling. And this temperature is actually, as a thumb rule, you can calculate if your annual maximum temperature is, let's say, 47 degrees, which is there in Jaipur, where I come from. And if my annual minimum temperature is, let's say, 3 degrees, I calculate the mathematical average of this, which comes out to be 25. I dig a hole, measure the temperature 4 meters down the ground. It will be 25 degrees, which is the average of these two, plus minus 2 degrees. That's it. So it is a thumb rule which you can use to evaluate what is the temperature you're likely to get. And then it's more or less constant. So what I'm doing is what people do and what Sudhir has already shown, that you take this tunnel down the ground and then you pump air in this. So the only energy consumption this has is the energy consumption of the blower. So there are various forms in which this concept is used. Most common one for air is a horizontal laying of pipe. But yes, people have tried using a vertical looping also, using a slinky kind of or a spiral kind of arrangement, and even a helical kind of arrangement. It depends upon the space availability that you have. Okay. And same concept, if I'm not blowing air, I'm flowing water in this, becomes nothing but my ground source heat pump, which is talked about as a very efficient option. So the concept is same, that if I have excess heat, I throw it into the ground through this heat exchanger, which is through a pipe. And if I have excess of cool, I grab heat from the ground, which is again through the pipe. Okay. So I'll straight away go to what are the design issues. One is the depth. it depends upon the soil property. So first is soil investigation is a very important aspect. People normally do this mistake that they don't get the soil properties investigated, and then later on they claim that this is not working. So first is determine the correct depth. If your soil is less conducting, you may arrive at a different depth which is required. And if your soil is very conducting, highly conducting, moist, then you may go for a different length. Okay. Length of pipe is quite important. In fact, there are examples where people have just laid a 10-meter tunnel, whereas there are examples in the country where you have 1 kilometer long tunnel also. Okay. The tendency of temperature heat exchange is basically using an inverse exponential curve. So after a certain time where the exponent curve touches its knee point, the cost economics of every incremental length of pipe deteriorates. And it is so you have to cut down where the economics works out. Maybe at that is the right time when you decide whether to go for a one pipe or a parallel two pipes. So that is where the optimization and the calculations play a very important role. Sometimes we, like in Jaipur, we have determined that an optimal length is 60 meters. So if you have more than 60 meters, you better have, if you have to blow more air, you lay parallel pipes. But when I say parallel pipes, first of all, I have diameter of the pipe becoming very important, because diameter of the pipe plays the important role in determining the energy consumption of my blower. If I'm taking too small a pipe, my friction losses would be very high, and therefore my blower capacity, the energy consumption in the blower, would be high. Whereas if I have to blow the same amount of air through a smaller pipe, my velocity of flow will increase, which may increase my heat transfer. So again, there is an optimization of heat diameter of pipe. You increase it up to certain stage, it helps, but if you increase it even more, it deteriorates. So there is again an optimization involved in that. Number of pipes, as I said in the beginning, that you have to cut down at the optimal length, and therefore you have to decide how many pipes you are there. Basically, what matters is surface to volume ratio of the pipe. More is the surface per unit volume of air flowing through the pipe, better is the heat exchange, better is the performance of earth air tunnel. And therefore you need to play around between the number of the length, diameter, and therefore determine the right number of pipes which are to be laid. But when number of pipes are to be laid, people do another mistake. They lay the pipes very closely. So what happens is between two pipes, there is not sufficient amount of earth which can absorb heat. And therefore one pipe has a thermal interference with another pipe, and then again, the system doesn't work very well. Then we have soil properties, as I already said, conductivity, specific heat, and density is most important. Material of pipe, people have a lot of confusion. Of course, metallic pipes have more conductivity as compared to HDPE, which is again another alternate. But frankly speaking, if the wall thickness is not very high, the material doesn't matter much. We had a parallel setup of steel pipe versus HDPE pipe. Of course, there was a difference of 1 or 2 degrees in the outlet temperature, but yes, not much. So if your cost economics works well, maintenance works well, you can go for HDPE pipe, which many people are doing. Some projects have used cement pipes also. Air velocity, as I said, is a very critical parameter because it governs your energy consumption. Not to ignore, if you are continuously operating in an earth air tunnel, the performance would deteriorate over a time. I repeat, if you are continuously operating it for 4 hours, 5 hours, 6 hours, what happens is because of the thermal resistance, the heat transfer, heat has crossed the pipe, but it is still in the soil. It has to go further, far from the pipe. And it takes time. It's a slow process, relatively slow process, especially in the soil if the conductivity is not very good. So after some time, there is a 20%, 30% performance deterioration in the cooling effect that you have initially, and that is to be taken care of in designing. Coming to the next point, which has been given to me, is the evaporative cooling. So there are 2 types of systems in evaporative cooling nowadays. Of course, the principle is we all have desert coolers in our homes. What happens is there is a pad over which water is trickled, air passes over it, and therefore, because of evaporation, heat of the air is absorbed by the water, and basically what happens is the air is getting cooled down. That water which evaporates leaves the surface, and therefore the water that you get down in the sump is also cool. So you get 2 cooling effects. One is ignored usually, one is utilized. So you have cool fresh air which we enjoy, and this system works well in dry climate. Okay, but this cool water in the water tank is also a good cooling source which is normally ignored. So what is done in the cooling system, direct evaporative cooling system, is that you have evaporation. So on the y-axis, you have moisture content. So moisture content increases, and therefore in humid climate, when we use the evaporative coolers, people do complain that it's not working very well. So nowadays, over past 10 years or something, a modification of evaporative cooling has come, which is direct indirect evaporative cooling system. Now what we have is we have two air streams. So the primary air or the secondary air. So the secondary air is basically what it is doing is you can say these are two coolers side by side, one after the other. So one cooler, what it is doing is it is just cooling the water, and that water is passing over the plate heat exchanger. And on the other side of the plate, my air is flowing. So air from the first section, which is the orange one, to the blue one, is not getting any additional moisture. It is just getting cool, which is called sensible cooling. And then after that, whatever remaining cooling effect is to be obtained, you can have water-based evaporative cooler, regular cooler, and then you can get. So the advantage is twofold. One is you get more cooling. As you can see, instead of the first one, I'm going to a lower temperature. So I get a temperature, more cooling effect. Another is I'm getting less humidity added in the air, because my first stage was without adding any humidity. And therefore, I not only achieve a lower temperature, I can have it perform during the humid days also. Little bit humid days also, it performs. And third, but most important thing for sustainability is I'm evaporating less water. About 30% less water consumption is there in this second type of evaporative cooler, which is direct indirect evaporative cooler. So this adds to sustainability, and these options are now quite common. In fact, there is a new version of that. After that, people have integrated a regular air conditioner, which is called DH system. So it has three systems depending upon the climate, because in very humid days, even this direct indirect doesn't work very well. So then you bypass these two stages and use a regular air conditioner. So what we did was we tried to integrate our earth air tunnel with the evaporative cooling experimentally. And then what we found was, like shown in this graph. So the brown bars are the hours which are comfortable using the earth air tunnel without the evaporative cooler. But yes, as you see that in April, as the ambient temperature increases, the earth air tunnel was not giving sufficient comfort. So I started utilizing evaporative cooler also. So whatever free cooling I was getting through the tunnel, I got. But after that, I started using evaporative cooler. So as a combination, I still got more than 60% of the hours being comfortable. But again, as the temperature increased in May, June, that was not falling sufficient. So what we did was basically in June, July, and August, and September, you don't have any option. The hours are uncomfortable. So maybe you need to have another air conditioner working in conjunction with that. There is no harm in having these systems. And that's why the new commercial systems having three stages, indirect, direct, and DH stage, these have come up in the market. And again, as the temperature goes down in winters, we are seeing a very beautiful free heating effect. So space heating also can be done using earth air tunnel. What we also tried was that this is the experimental setup shown in the air conditioner. So we tried to run it, what I was showing, that all the three stages can be run together. We have experimentally done this, and we have shown up to 30% of energy saving over conventional use of air conditioning. The last thing which I want to touch was radiant cooling, and it is catching up these days, because most of the sensible cooling is basically done through radiant cooling. Radiant heat transfer potential is many times, few thousand times more as compared to conduction and convection. So what we are doing is we are having three types of radiant cooling systems. One is the radiant panel. So these are like your false roofing. From beneath, you can't make out a difference. Okay, there are copper tubes in which chilled water is flown. So the panel is cool and it sucks the heat that is released inside, or that comes from the envelope. These pipes are also laid in the roof slab, and therefore that is another type which is called thermally activated building. And there is another type, people are having chilled water or even cool water, not chilled, it is cooled water. Water at 15 to 16 degrees centigrade is good enough for this. So all the three types of systems are there. What they do is they basically are having active integration of active and passive. Now what you can do is you can have a chiller, but if you are getting from geothermal, which is earth air tunnel, if I am getting sufficiently cool water through the earth air tunnel, I can directly circulate that water through the pipe and then getting my heat absorbed through that. If I don't have earth air tunnel, I can use evaporative cooling, meaning my cooling tower. Cooling tower is also evaporative cooling. So I can use cooling tower here directly, and then I can circulate the water, which I get from cooling tower, through these tubes, and then I can get cooling effect. And if these two are not doing sufficiently, maybe in very humid days, then of course, for the remaining time, I can use a mechanical chiller or a DH system for that. The biggest advantage, the big advantage, not biggest, but the big advantage is you get a very nice ambient indoor air quality. Indoor environment quality is good. sound, the background sound that you get with the air conditioner goes away. Okay, the spatial distribution of cooling effect is excellent, and definitely energy saving and use of refrigerant and all those things are there. So I summarize my presentation with this. There are several passive cooling options available for the building, and their application in modern buildings has its own challenges. But yes, there are a umpteen number of examples where successful demonstration has been shown. There are several compressor-less or refrigerant-less cooling options. Okay, we should make use of these, and evaporative cooling definitely is one of those. But what works best in modern context in modern buildings is if you can somehow integrate what options I have quickly shown, integrate active measures with passive measures, because people are not really so tolerant as they used to be earlier. So if you can't compromise on your comfort, I think, in my opinion, integration of active and passive cooling measures is what works the best. And if you do this, you considerably save energy. You have protected ozone layer depletion, global warming, and your indoor environment quality is best. Last but not the least, if you're adopting these measures, Energy Conservation Building Code, you are given a bypass from compliance of Energy Conservation Building Code, which is again another most important, one more important aspect of it. With this, I sum up my presentation. Thank you very much.
Thank you so much, Jyotirmaji. This is fascinating to understand from you this whole integration of active and cooling approaches and what you have the three different approaches that you have demonstrated. And what is really very amazing is that you have kind of demonstrated it with actual data to show that how the improvement happens, but also how you reduce the air condition hours and you can apply that so flexibly. I know you are in a hurry and you have a meeting to go to, but just because you will not be here, so just before you leave, a very quick reflection that now that you have demonstrated and you've shown the practice, right? How do you see the response from the construction industry? Do you feel that this is replicable, scalable to the level that we want to see it happen? And what is needed for that?
We have helped some projects implement these concepts, and they are doing it. The only thing is, from the promoter side, it needs little kind of daring attitude or ready to fail kind of attitude. People they don't want to take risks. So first of all, they have to be little experimental in nature, but those who are, I think there are a number of places where these systems are working very well. So the only thing is, be a little open, don't be stereotyped that, okay, only refrigerant-based air conditioners would be the solution. I think these systems are easily replicable. The only thing is they need to be designed cautiously. And the design skill and the implementation skill is not available very easily. That is the bottleneck. So if people know how really good to design a good system, they are working.
Absolutely. I think you made a very important point that we may give them the solution, but to make it scalable, we have to build their capacity and skills to take that forward. So absolutely, that's, thank you so much, Jyotirmaji. Thank you. Really, I know you need to go. So we're not.
Thank you. I'll hang around for a few minutes till my other meeting starts.
Sure. Thank you. So thank you. So now to take this conversation forward, I'll ask my colleague Rajneesh to share with you that what we have done in our campus, Anil Agarwal Education Training Institute, AATI, near Alwar. And just to make the point that even when we are getting into this issue and investigating it so deeply, but we also strongly believe that we need to practice what we preach. And that's what Rajneesh is going to share with you, that how are we practicing this? Rajneesh.
Thank you, Anumita. Anumita has already given you the philosophy that why we wanted this institution and why we wanted all these technologies and system to be in place. Because largely, as Professor Mathur has also said, that you need somebody to really put a first step forward. The CSE thought that this is the first step forward we need to bring in. The philosophy revolves around the three major challenges which we encounter or worked around with. One is the first stage is where we actually worked on to reduction of, or rather enhancement of water natural elements which are there. So your need, when I'm talking from the cooling requirement, I look at the natural system. So passive measures were looked at. So the moment we looked at passive, we looked at microclimate enhancement, we look at building forms, we look at envelopes and all, where in envelope, we try to look at various materials and things like those. Now, this is something where we try to reduce the impact or the requirement for cooling to whatever level is possible. Now, next stage which comes is where the environment is going to help me. The environment, for example, the renewability part of the cooling which is available in the environment. So maybe evaporative cooling, or there is something else which is available in the form like somebody has used in their project as a geothermal or some other else form of renewable energy or format which is available. We try to utilize that. And then the third important step was to look at efficiency. And efficiency also with a responsibility. As you see on the screen, that we have tried even our hands on to natural refrigerant as one of the methods under that. So I'll give you a little more overview, but run you maybe another 5 minutes. I'll give you a little overview of what we are trying to. Sorry, little glitch, the slides are not changing. So what exactly we have done is the very first step which we are looking at is the where we try to look at microclimate enhancements. Now, under this microclimate enhancement, first of all, it was important for us to work at, looking at what is the site which is available to us, the variation in the site and the chronology which was there. So first thing which was look at that we wanted to enhance maybe the water bodies, retain water for a longer period, have more greens, increase the permeability part. So because these are microclimatical areas, because these are the areas which are lifelines, which are all around us. Whatever is available as cooling outside is the strength which is there in the site. So first step was that we started planting this area. So because as we are there in the Aravalli zone, we know that the green cover was not that great. Water retention was always an issue. The soil binding capacities were also poor. So we started investing into green. So it's not only 1%, the complete CSE started extensive plantation drives in this. Then comes where the structure of how the structure and the philosophy will flow. So we largely look at, because the climate is harsh where we are located at, we try to look at a narrow courtyard and maybe the favorable orientations. These possibilities were being looked at. So we try to structure ourselves in a way so that there are shades, and the enhancement of shades in the beautification of these shades which is there could be done along with it. So this is one of the examples where the administrative block is, where we not only enhance the shading, but we bring in the green as one of the important features, which try to regulate the microclimate, which is inside into the structure. It flows through. So the energy which is available outside enhanced with these measures, and then it's flown into the interiors of the structures which are available. So then comes largely the envelope materials and shading. All these parameters are looked at. Now look at how we beautifully try to work on this, that we try to cut the harshness of the sun, which is on the exposed part of the structure, by bringing, maybe initially is to bring the buffers. So toilets, your staircases, any of these are on the harsher side of the sun. Then we even try to look at the combination with the material. We experimented with the ramp, then we graduated to AAC and bringing certain amount of insulative properties also. So the philosophy is that we brought buffers in. We got the harsh sun which is on the rooftop, we got it cut through by reflector roofs as well as through insulation. Then we worked on to the envelope in terms of walls and as well as the shading factors around it. Window walls, for example, has been kept at 30. Then whatever the possibilities we could do, the glazings and whatever were done was double glazed, so that our values of heat ingress which is going to come from any side of these envelope could be reduced. And that too, these were all windows were covered properly, so that the sun which direct makes incidence of sun could be reduced, so that the heat should not flow in the way it is. Then the seasonality, as Professor Mathur has already given you that strength which is there in the season, we need to utilize that. So we looked into all the 4 seasons which are available: summer, winter, autumn, spring. So then what are the possible strategies which we're going to work around and bring what solutions? So maybe what we have also done is 2 to 3 months is the dependency on the air conditioner. Rest most of the time we run with whatever naturally the systems are available to us. Then we augmented it by bringing whatever the energy which we have to consume, maybe primarily for air conditioning, we need to bring it down. So we started investing onto solar as well as other possibilities where the energy could be worked at. The one example is that the waste heat which is going to flow into the environment by running this. So one is that we counter the energy. The second thing is the heat. in any case, because we are going to displace the heat by running the air conditioner. So what we have done is, we have done a heat pump analysis. So we have a heat pump, we have a heat exchanger. Primarily, whatever the heat would have been thrown into the environment has been utilized to maybe hot the water for kitchen requirement as well as for the bathing requirement. Then another area where we intervene is about the natural refrigerants. So one part of the structure or of the complete area has been experimented with a natural refrigerant, largely because you require a little more controls, there are more flammability and other issues which are there. But still, we experimented to have an understanding that how this system works, how these functionalities are there, what are the possibilities which will be taken up on this. We do have a 3-stage cooling system, which Professor Mathur was explaining to you. I can show you, this is how the air handling unit, which runs on direct and indirect cooling. This is where the evaporative pads are there, and as well as there is a stored water which is there, which largely gives you maybe whatever months I was telling that where we are not using air conditioner, because beyond this, if I look at the 3rd stage or the last pocket or the cabinets which are there, they are for where the chillers are or the cold pipe was coming. Otherwise, largely throughout 7 to 8 months, we are running with these systems, either with direct or indirect, and as well as other possibilities were available. So we got the system functioning. It's almost 7 years where we are running this. We do have a lot of, you can say, the good experimentations, as well as there are a lot of good viewpoints from the occupants over, because it's being used as a training center. Where not only us, we stay there. There are many people from across the country come and stay with us, and they have given us a very good feedback about it. Over to Anamita.
Thank you so much, Rajneesh. And while listening to you, it just struck me that the moment we begin to take this kind of system approach, and if you can recall that what a rigorous, intense exercise it is to understand a site and an area from all aspects to be able to do this kind of planning. Understanding the site, the microclimate, the seasonal variations, where the sun's coming from, where the wind is blowing. So, and I just remember what it meant for us, right? And I think that's the knowledge that we really want to see that is getting across and owned by the community across the country. And that's why this conversation is so important today. So moving forward, I would now like to invite Mr. Ashok Singh, Chief Operation Officer from NIT University, Neemrana. And Ashok Singh ji, you have this deep experience of operating this air tunnel system in NIT University. And therefore, we would really like to understand from your experience what insight you would want to share for us to take this kind of innovation forward.
Thanks and good evening to everyone. I am not an expert. I would like to clarify right in the beginning, but I'm a huge practitioner. At the university, we have this system running for the last 14 years and a tunnel network of little more than 1.8 kilometers on the campus as on date. So I just wanted to give few insights where I have heard both the former speakers and your presentation. We are generally on the same lines, but few practical aspects that we have experienced is what I would like to bring out now. And at the end, sum up as to what we need to do further. So Neemrana is pretty much between what Nimli and Jaipur is. So the temperature variance is 45 degrees in the summers to minus 0.5 in the winters is the range that we have. And the humidity, which is a very important factor which we'd like to bring out as a practical experience, is about 1 to 5% in winters and 85 to 90% in the monsoons, which is the trouble creator. So as all of you use it, we also use 3 elements of nature: earth, air, and water. And 4 meters depth are our Hume pipes, and we run it 100 meters for heat exchange. And we don't have pipes running very close to each other because to prevent that interference that was talked about. And our experience is that the tunnel which delivers 25 degrees from the months of October to April reaches 27 to 28 degrees in peak summers. So that is the temperature inside the tunnel that is delivered. And of course, earth air tunnel for pre-cooling. As I said, evaporative cooling for basically initially for filtration of the air, then balancing the humidity, humidifying or reducing, we'll say how do we do it, and reduce temperature. So we have added displacement ventilation to further reduce the energy consumption. So with whatever the air inlet comes in, we have seen on all the diagrams, and air goes out from the top. Therefore, we don't use any additional power or energy to evaporate the air. You have shown that photograph also in your presentation. So in this concept, firstly, the air is 100% fresh air system, so no recirculation of air is involved. A very high indoor air quality, which is less than PM 2.5 of 10. And reduction in power consumption. So the saving is around 60% as against the conventional air conditioner. No greenhouse gases produced, so we reduce the carbon footprint. And ejection of heat in the atmosphere does not take place, thereby heat buildup on the neighboring areas is further reduced. And one point which you also mentioned, east-west orientation of building, so that heat buildup is on the smallest cross section of the building. And of course, you have also said that locate your staircase and the toilets on the external east or west side, so that that further reduces the heat buildup. Now, as far as the running is concerned, we run our air handling units from August to September. At times go up to October. Well, as the ambient cools down, the other aspects of the building have been designed in a manner that you don't breathe this air. The building remains cool. Use of a fan is adequate to give you comfort. Now, our problem comes in the high humidity season, that is from mid-June to, I would say, mid-September. So these 3 months, what we have done, we have a chiller coil, which is 30% of the inlet or the outlet at that time, through which we utilize the chillers to provide a better comfort during these months. In the summer months, in certain buildings, we have the cooling towers. So apart from the delivery between 26 to 30 degrees in all buildings, we achieve one more degree of comfort by using the cooling towers. But in high humidity season, I said, it creates a problem. Now, what has helped us in further reducing the heat around the area? Because if you compare between Neemrana town and our campus, which is separated by just 2 kilometers, there's this 2.5 to 3 degrees difference in temperature. So as you drive down from Neemrana market or the town to the university, you suddenly find a whiff of cold air. That is because over the period of last 10 to 12 years, we have adopted the area outside the university, which is on the Aravali Hills, which is protected by the Aravali Act, so no construction or development work can take place. And we've planted over 1 lakh trees in this period. And that has created a microclimate around the campus. So that further enhances 2 things. Firstly, a cool temperature. Second, reduction in pollution to a very large extent. So people traveling from Delhi and other places, when they come to the campus, they naturally say, oh my goodness, it appears that we are breathing fresh air. So that is the difference it has made. And I in my recommendations, I'll bring out as to what do I mean by this. The carbon, this microclimate has contributed to approximately 24 kilotons in carbon sequestration over last 10 years. So the other aspect about the layout of the buildings, I said one is orientation, second is close tight layout between the buildings. So shadow of one protects the other. Next part is we have retained and tried to retain the natural flow of water and layout of ground to the extent possible. So the courtyard that you had shown is not an architectural marvel. Actually, it was a valley between two sand dunes. You retained it like that and constructed buildings accordingly, so that in this place where the rainfall is very scanty, the natural flow of water, whether overground or underground, is not greatly disturbed. So that helps us in sort of conservation of water to a large extent. Now, over a period of time, 7.5 lakh square feet is what we are covering in the 7 buildings that we have. And we monitor the energy saving in all buildings. So our experience is in the residential areas or the hostels, the saving is around 61%. And in the academic blocks where, larger machines and larger number of labs and other things are utilized, the saving is around 54%. So averaging to about 60-odd%. And even while we are delivering air to various buildings, because the air shoes are at the ground level and transfer air to top. So computational fluid dynamics to design the masonry building so that the distribution of this fresh air is equitable at all the floors. Otherwise, when you pump up, the lower floors always take more. So the design has been made of the ducts in a manner that we deliver equal volume of air in all the rooms on all the floors. And at times, when we see that the chillers are not required much, we increase the CFM so that chillers are not required to be run, and that provides sort of comfort. I would, in the final point, say that firstly, we are reading every day, new IITs, IIMs, and AIIMS are being created, and everywhere we are reading that so many air conditioners have been approved. I find it very ridiculous because some of these IITs are being created at very good environmental areas. So we should be able to take advantage of the local conditions over there, make maximum use of the 5 elements of the nature for cooling rather than blindly using air conditioners, which is doing the damage that we all understand. I also recommend that in whichever fora we want to discuss and talk, there should be a compulsory creation of green zone, whether it will be a residential complex, a commercial complex, or an educational complex. So these green zones should be made absolute compulsory, because that's what creates the microclimate, as you have done at Nimli also. And even where we are using air conditioners, I think the design should be such that nobody should be able to put the temperature below 24 degrees. And the lifestyle, I find in many conferences and meetings that I go, the temperature of the room is 18 degrees and everybody is putting on jacket, coat, and tie. I fail to understand why can't we use open collars and normal shirts and keep the temperature at 24, 25. You'll feel equally comfortable. So I mean, we are blindly trying to copy somebody in the form that it is a corporate culture. One bank fellow came here, one bank program came. And when I was telling them this is what our system is, some of them said, sir, we are from the banking culture and we need to work at 18 degrees. So I had a hearty laugh. And this is what is there in the mind of Indians. We as Indians, we are going to land up in trouble in the future as the requirement is going to come up. And finally, I would say revival of the water bodies. We are killing all the water bodies in all urban areas by covering them up and trying to build up. We have seen what happened in Chennai 5 years back when it got flooded. Rain deficient area got flooded. Okay, we have seen what is happening in other cities very closely. So on the campus, we are very mindful of ensuring that every drop that comes in is recharged through numerous number of water harvesting recharge wells. I would like you to visit my campus and see my sewage treatment plant. The students of the university has named it as Temple of the University. We maintain it like one of the labs of the university. To be mindful of keeping it in that manner, my entire operations team of 30 people takes breakfast inside the STP, which is 2 stories below the ground, first Wednesday of every month. Thereby, we are ensuring that whatever goes in, 97% is utilized. My entire water requirement of going 600 meters deep on the Aravalli Hills through drip irrigation is all utilized from this STP. Not a drop I use on this 100-acre campus and the 150 acres that we have, I would say, encroached upon for greening on the Aravalli Hills is done from any other source. So this is these are the methods by which I think we can ensure that we can remain cool, use the natural resources, and still survive. Thank you.
Thank you so much, Ashokji. It's a great message from you. And it's a great example of how, our space can be transformed by just taking advantage of the local microclimatic conditions or overcome the limitations with design approach, learning by doing and practicing and inventing your new solutions. But the great learning that we have from you, and this has to be taken forward and be spread. And I really liked what you said, that it's also about our behavioral change. And this reminds me of the bush shirt rule in Japan, that we really don't have to dress up but dress down, but be comfortable and be aligned with our local microclimate. So certainly we'll come back to you, Ashokji, soon in the next round. And so we'll move on to the next conversation, and then we'll be back to you with new questions. So now I would like to invite Mr. Mahesh Vasavanna. And Vasavanna ji, I know that you have been so deeply involved with our NIMLI project, and you have helped to design this 3-stage cooling system. And there's a huge learning and innovation that's possible in that sector. So please, we would like you to share your insights on that.
Thank you, Anvita. And thank you all and good evening. Mr. Rajneesh actually has already explained about CSE. I would like to share the presentation. Is it?
Yes, we can see your screen.
Yeah. So, yeah, this is the design stage that we have involved, MACDIBER. So just to give a brief actually about MACDIBER, we are a 20-year-old organization, and we have done buildings which are net positive in terms of energy and water, and also MEP design services. Sustainability and MEP is our core strength. Just to focus actually on this project, this is Anil Agrawal Center at NIMLI, where the temperature actually is around 43 degrees centigrade in summer, and monsoon it goes to 35, and winter it is 7.8 degrees centigrade. And these are all the weather details, like a wet bulb and a relative humidity. In summer actually it becomes very dry, and monsoon actually it is humid, and winter actually also is cold. So you have 3 seasons. One is summer, you need to air condition or use an alternative to air conditioning. But in the monsoon, you need to dehumidify the air, and in winter actually you need to heat the space. So this is a kind of a climate actually where you need all the system to get what is needed actually for the thermal comfort. So we in initial days we did the analysis, like assume that in a base case you have the environment which is like a concrete pavers, asphalt road, and absorptive surfaces. So we did this heat aligned effect study, urban heat aligned effect analysis, versus what is actually is there in the NIMLI is green pavers, vegetations, SRI roofs. So there is a 6-degree temperature difference between if you would have constructed a building with a concrete pavers, asphalt road, and then it's like a concrete jungle, versus what is incorporated actually in NIMLI is green pavers, vegetation, high SRI surfaces, and water bodies. So that basically there is a difference of 6 degree, which is reduction in outdoor air temperature, ambient temperature, compared to the conventional, buildings. So this is what actually vegetation, you have green pavers, and tile roof, and also we have a water body, and then a lot of solar roof and shading devices actually for the buildings. And what we did actually at the first when we discussed actually with the CSC management at the time, Sunita Narayan actually was involved in this project, and also with architects, that how to orient the building in such a way that we reduce our operational energy consumption and also reduce our heat loss. So assume that if you would have now this building is oriented actually towards north and south, the larger facade actually is oriented towards north south. Assume actually you would have oriented on the east west direction. So east west actually becomes like a 90 degrees, that is a conventional building, versus if you would have designed against the east west, if you are designing actually with a north south, so there is a 12% reduction actually in the operational energy. Just by orienting the building on a right direction, we are able to reduce this. Simulation we have done actually for 8,760 hours, and then basically find out that what is the best orientation, east west or north south or northeast, in those angles that we have done. So there is already operational energy consumption actually by 12% reduction, and doing a heat island effect study, having a green pass, so there is a reduction actually of the outdoor temperature by 6 degrees centigrade. And what other thing that we have done is we have done the extensive shading to the building, so that two things that we wanted to achieve. One is the daylight, the light, the direct sunlight actually should not touch the glass, so that it creates a heat. And at the same time, we also wanted the daylight, it should be daylight. So the two things actually which is achieved in this building. One is basically to maximize the daylight. So in the daytime, we no need to switch on the lights. And also at the same time, we wanted to shade the building in such a way that, the glass obviously, receives a lot of sun and then heats up the space. We basically reduce the heat gain, to the building by using the shading devices, and also get the daylight into the space. So the third thing is what we have done is basically about envelope. In a conventional building, you use a 200 mm brick or a concrete block, both the side plaster, and 200 mm RCC, 150 to 200 mm RCC, and a clear glass and no shading devices. Versus, what we have done is a AAC block and insulation actually to the roof, and also a double glazed shading, double glazed glasses with the shading devices. That there is something called envelope heat gains. The heat actually which is coming from the wall, from the roof, from the glass. So that is the heat, this is called a solar gains. In a conventional building of this size, in an academic building, the conventional building actually will have a 4 watts per square foot. The 4 watt of heat actually which is coming to the building through envelope, from the roof, from the facade, from the wall, from the glass. So in this case, we are able to reduce to 0.8 watt per square foot. There is a 80% reduction of heat load just by doing a right orientation, shading the device, the building, and also having a double glazed low E glasses. So four we are able to reduce actually to 0.8 watts per square foot. So that is a there is something called RETV or OTTV, overall thermal transfer value. So that from 4 actually it has been reduced to 0.8 watts per square foot on a built up area. So, and also if you look at that we also studied the comfort chart, that assume that windows are designed in such a way that actually that we should be able to open the windows and allow the wind to pass through, and orient the building in such a way that we should be able to allow the natural ventilation to happen. If you have a in a 0.1 meter per second versus a 0.8 meter per second the velocity, so there is a the comfort band also you can increase. So it means that at the air temperature of 29 degrees centigrade, you are also still comfortable, versus 25 degrees centigrade actually with a 0.1 meter per second. So the thermal comfort always, it's not just only to do with the temperature, it also to do with the the humidity, it also to do with the air velocity, and also the flow value, and then the work. So we use this system to identify what is can we increase the temperature, instead of setting a 24 or a 25, can we make it 27 and 28? Are we still comfortable? So that is the one actually that we checked. So after doing this, first actually we did the on the outdoor climate, we basically wanted to reduce the outdoor climate temperature by 5 to 6 degrees centigrade by planting trees and having a sustainable landscapes, urban drainage systems, and things like that. Second one is orienting the building actually towards the north-south. The third one is having a right building materials and also having a shaded windows and also having an insulation actually for the roof and reflective paints. So, and the fourth one is so after that, from the conventional building materials that versus we needed a 150 tons of air conditioning. So that has been reduced to 101 tons, 100 tons approximately. So that basically there is a reduction of air conditioning load by 32%, which has happened. Then with the reduced air conditioning load, we can come up with many solutions, cooling solutions. One is, why to air condition, like a conventional air conditioning, can we look at some other options like in a previous discussion, actually, the professor actually already told about the indirect evaporative cooling and a direct evaporative cooling and also chilled water coil. This is the option. With a chilled water coil, actually with a reversible heat pump chiller, it can also produce chilled water. At the same time, it also produces hot water and also produces domestic, hot water requirement during any time. So this is the system that we have devised. And so if you just look at in summer, indirect evaporative cooling is on, the direct evaporative cooling is on, and the chiller is off. So basically, you are able to get the comfort with the indirect and direct. And in the monsoon season, where the humidity is more, so the indirect evaporative cooling is on, direct evaporative cooling is off, because in direct evaporative cooling, you actually adding the moisture directly into the air. So basically, that is off, and the chilled water is on. That's when actually the chiller comes on. So this is the system that we have designed. To basically, it is basically a mixed mode, cooling system or a heating system. In winter, you need a hot water, and so the same chiller, can produce hot water. The same chiller also can produce chilled water. So with this, if you are a conventional design versus an optimal design versus what is proposed, that we are able to reduce our electrical load by 59%. By using a mixed mode cooling system. So actually first we have reduced the air conditioning load by 33%. So we could have gone with a conventional air conditioning system, but we went with a mixed mode cooling system. So that is able to reduce our electrical load actually by 59%. So this is what actually, in a conventional building, 600 kilowatt actually will be the electrical load. In an optimized building, with a conventional air conditioning, it is 415 kilowatt. It is being brought down to actually to 284 kilowatt. So that is basically 2.8 watts per square foot. In a conventional building, usually it will be around 5 to 6 watts per square foot. In this building, that we are able to bring down to 2.8 watts per square foot. So that is the electrical load. Okay. So yeah, then basically with a reduced electrical load and reduced DPI, we went actually with a solar PV. So that is able to generate its entire electricity. It is a smart grid system. So that is able to generate the entire electricity for the whole campus. So this is about my presentation.
Great. Thank you so much, Mr. Vasuvarna. And we know, because we use that campus and what it means to live and brand experiment. But when you also show that what's the exact number, the quantification that we have done in terms of savings, in terms of reducing the electric load, the air conditioning requirement, I think that's what really convinces people. And we know that what a center of attraction this system is in our campus for all the architects, planners, engineers, construction agencies who visit our campus. And that's how I think we need to create more such demonstration centers, but also generate the data to convince that it's a working and a real solution. So great, thank you so much. So we will come back to you, and I'm just looking at the time. We've got two more presenters. So I will now invite Mr. Neeraj Manchanda. Mr. Manchanda, you have this great experience of designing passive downdraft cooling system in IIT Gandhinagar. And we really would like to understand from you your experience, learning, and the replicability of this experiment.
Thank you very much. I just would like you to confirm that you're able to see my screen now.
Yes, we can.
All right. It's been very interesting listening to all of what you and your colleagues have been talking about, and to the earlier presenters. So there is a lot of common threads of understanding and of action, both that inform sort of all of what we have seen so far and some of what we'll be seeing now. What I'm going to do is I will quickly, having listened to what has been discussed so far, I will, for this particular presentation, I'll stay away from the numbers, but I'll just try to, sort of talk about the overall sense of how the whole thing integrates and what we did at IIT Gandhinagar, both for the hostels and for the guest house. Before I sort of start the presentation, I would like to basically say one thing, which is that, before, up to a certain number of years ago, let's say, when we discussed ecologically responsible design, I would use 3 E's, energy, ecology, and environment. But once this pandemic has come and sort of gone in many senses, I am no longer able to use these 3 E's. I've been using 3 H's. And those 3 H's are human, health, and happiness. And the reason that I felt compelled to do this is because I am not able to view, ecologically responsive or environmentally sensitive design in isolation of other things. By this, I mean that if one were to have a physical envelope that is thermally very efficient, that does not give us the whole solution. The whole solution needs to be a fully integrated one, and sustainability in many senses, needs to start with the idea of social and human sustainability. So I don't know how well I've been able to explain this shift in focus, but let me just get to the presentation and we can talk about this later if there is time. So on this slide, you will see on the bottom right-hand corner, a generic sort of pattern, spatial pattern, which is a doubly loaded hallway or a corridor. And in the case of IIT, what we decided to do for the guest house is to fracture this and go back to inserting open space in between, which is not something that we have not done in the past. In fact, in traditional morphology and design and building systems on the subcontinent, this is a very prevalent practice, has been a prevalent practice. And so landscape becomes inserted into the middle. So this slide perhaps captures the entire story very effectively. The idea was to actually use a vertical and a horizontal garden both, and using these 2 features, make the connection with location and also make this thing develop into some sort of a microclimate performance that can give us preemptive sort of cooler and a more tempered environment, both light-wise and temperature-wise. So this was the whole narrative. This is a sort of a top view of the completed premises. I'd like you to just remember the density of this trellis work that you can see in the middle courtyard over here. Going forward, this sort of tells you the intensity of landscape thinking that informs the entire project. We are inspired here by the morphology of Ahmedabad itself, which, as I will show you a couple of slides down the road, which actually, so I'll talk about that a bit later. So here is a picture of the completed project, which tells you what its overall Shakal Surat looks like. It's actually done with SCC, which is self-compacting concrete. And one of the things I'd like to sort of mention here is, or I'd like to point out here is that, you know, if you see, you're not really able to see too much of glass right on the surface. Now, what that means is, and this is something I'd like to sort of promote, subcontinentally, I think the whole business of fenestration, or the whole business of how we articulate the external skin, you know, there are complexities that we can build in over here based on an understanding of, you know, sun movement and, you know, incident solar insolation, which are not very complicated. And I think some of the more thoughtful projects that one finds, one is able to see that just by tempering, you know, incident insulation in this particular manner, a lot of positives can be obtained. So this is, as you see, as we go around the building, you will see a fairly well-developed understanding of how fenestrationally we are able to control the sun. This is on the, you know, southwestern side, sort of based on simulation and based on calculation, how we're sort of putting in protection on this side. And you can see how much of the window is actually being protected, even though we don't have a horizontal slab which projects out. Both we didn't put it in because it was adding to a built-up area. It was also a maintenance issue in terms of, you know, who's going to go out and clean it. So what we preferred to do was a combination of a small chhaja-like projection and a horizontal band out on the outer surface, and together these are able to provide fairly good protection to the sort of internal window surfaces. So this is actually from the time of, this was actually won in a competition. So this shows you generally what we were sort of thinking about, the vertical and the horizontal garden, you know, density of plantation on the interior spaces. We were sort of, just to give you of how we were sort of visualizing the internal spaces. One of the things I want to mention here is that in this particular project, the idea is to promote chance conversation, because it is chance conversation or, you know, unintended interactions that spark off ideas. And, you know, IIT is a place where ideation happens, and we wanted to sort of encourage that. And the idea of being able to work with, you know, a tempered environment, not air conditioned, but where you can meet, you can sit, you can chat in relatively comfortable surroundings, even in things like undercrofts, as you can see over here. That was the main notion. So now if we just leave this all behind and we go to, so by the way, now you can correlate here on this drawing, the density of the trellis work that you saw in the site plan. And here I take you into the building so you can begin to see what sort of scale we have here, what height we have here, and how much of microclimate tempering is happening in the building. We use various techniques to sort of promote the idea of vertical garden here on the left. This is taken, this picture is taken a little bit early on after the building was completed. I have some more where you can see a bit better how this has happened, but fairly delicate sort of cable-based, you know, support system for creepers and vertical plantation to grow. And this is basically what we call the thin garden, the thin vertical garden. And this is inspired, as I was mentioning earlier, by the scale that we see in the poles of Ahmedabad. Here is another view looking into it. And this is the parallel that I wanted to draw. The poles of Ahmedabad are actually extremely masterful in morphology, in providing mutual shading from one side to the other. And that was a matter of great inspiration for us, and we derived some of our thinking from this. So this vertical scale of Indian morphology, of the subcontinental morphology, which is so locationally appropriate, is what we chose to sort of work with when we work this particular project. And it sort of creates some quite interesting patterns of light through the day. So it's not very boring to be here. You can just keep sitting and watching patterns and taking pictures. And you can see here the vertical cabling system, which then begins to support the vertical garden, which begins to grow. And this is a little bit later in the life of the project when the plantation began to take hold. And this was taken, I think, a year or two ago when generally the idea of the vertical garden began to slowly take some shape and sort of gives you the sort of look of the finished project. So here you can begin to get a feeling of the fact that, yeah, the vertical plantation is going up. So, and that when you look up is the sort of understanding you get of how the sun gets broken with the trellis work upstairs. And so this microclimate creation was kind of a successful strategy. The project has been extremely well received by the IIT Gandhinagar fraternity. I will skip straight to this, where in the passive downdraft, we have a capacity of about 750 students who are eating here in this mess. And the middle is the downdraft over here. On the sides are the warm air pickups. And this system tends to run between March and September. It tends to sort of start getting less in use as the months of July and August approach, but the thing stays in use till September. That's what IIT has reported to us. In fact, I made a call earlier today to the superintending engineer just to find out what the status is, and this is what he mentioned to me. And all of us, or some of us perhaps, we know how the whole drill works. So basically we have the mechanism to atomize air over here. The air drops down and you are able to sort of cool these areas with this cool air, and then you collect it and let it get it back out again. On the finished building, this is actually the sort of air collection thing. Inside, we have a very interesting detail you can see over here. There's another picture, yeah. So you can see here that what we have done is we've designed the windows themselves to work like baffles. So the cool air which is dropping actually hits this projecting thing as a baffle, and this is itself what carries the cool air in to this particular whole volume. So this is how it sort of comes in, and you can see over here the return air is getting out on the side. These are lures to pick it up and take it out on the escape chutes.
And it's fascinating design. And while listening to you, when you describe this, the whole aspects of the design aspects, you did it so thoughtfully with the science, the logic, the rationale, and also saying that how you have also drawn upon the local traditional knowledge to integrate that as well. And with that, the building doesn't look a concrete entity anymore, but a living entity to which the people can actually relate to. And what's fascinating about this design is that while you are ensuring thermal comfort, but it is also, there's so much of excitement in that space. There is no monotony anywhere. And you always see some surprise lurking somewhere in that whole space design. So I think, therefore, meeting the requirement of sustainability, livability, thermal comfort, but at the same time making the space so exciting for people who are using it. I think that's the biggest connect that we can make, and it's very powerful. Thank you so much for explaining this to us. So now, so we will now go very quickly to, yes, Mr. Gajanan Ram. You've been waiting long, and we are so happy to have you with us. And you are so special today for the simple reason that what we have heard so far from the experts, the practitioners, is the huge knowledge that we need to generate, and we are beginning to generate, that is going to define the whole built environment of the future. But as we have also understood that to be able to do that, we really need a very strong and extensive cadre of professionals with very, the right knowledge, the right skills. It's a new generation of professionals that we have to create. And that's where you play a very significant role. as part of the council, now that you are with the Council of Architecture, and you are going to play a very important role in defining the boundaries of curriculum that is going to generate that new skill. So what do you think is the way to integrate this new learning, the experiment, the message of sustainability, and the thermal comfort for all into the curriculum, so that, from the college itself, we are able to create a new genre of skill and professionals to take on the new responsibility. And I think it's a very appropriate question to ask you, especially today, which is a Teachers' Day. So that's where you are.
Thank you, ma'am. And I would like to thank Center for Science and Environment Institution for providing me an opportunity to be part of webinar on the topic Sustainable Space Cooling Solutions. I am delighted to hear a scholarly presentation on the subject, especially by Mr. Neeraj ji. I like to congratulate him for this, wonderful project. Neeraj ji, congratulations. As a town planner, heading town and country planning organization and holding the post of General Manager, Operation and Town Planning, Ranchi Smart City Corporation Limited, Urban Development Government of Jharkhand, I am also engaged as the Vice President of Council of Architecture, COA, New Delhi. The course of BR introduces sustainable development concepts through the subject of climatology, as we all know. Considering the present and forthcoming environmental scenario, there is need to reorient curriculum of architecture course. So, in this backdrop, CO is open to adopt methods for which would help in mitigation of climate change in BR course. The COA would look forward for recommendations in this regard from CSE. Training of practicing architects in personal capacity as well as government architects are essential to disseminate latest know-how in the field of sustainable development vis-a-vis methods for mitigation of climate change impacts. COA currently has 2 training research centers at Pune and Bhopal, where architects are being trained on various new topics of domain. COA is going to establish a new TRC in Bangalore soon. So we are very much open to take ideas from institutions like you on climate change issues, and we are very much open to incorporating in our BR courses. This is number point 1. In my official capacity, I can state that our office is engaged in framing, amending comprehensive building bylaws, and also GIS-based master plans of urban settlements in government of Jharkhand. In Jharkhand building bylaws, there are various provisions incorporated to mitigate climate change impacts, like mandatory plantation of trees, keeping green open spaces, following Energy Conservation Building Code 2007, harnessing solar energy for electricity in every building of more than 500 square meter, rooftop solar energy installation, provision for site level in greeneries, provision of rainwater harvesting in buildings more than 300 square meters. The department would be happy to incorporate new provision of suggestions in this regard of CSE in future in larger interest of mankind. So I can assure the CSE from the department that suppose you will give any suggestions, we will be amend our building bylaws for larger interest of the society of the Jharkhand and the state. So we are very much open. And I can say that the government of India is also having reform agenda of urban planning, like this sponge cities, conservation and renovation of water bodies, riverfront development, and creation of urban forests. So these are not the new subjects, but the thrust of government of India is also, and they are to leverage the funds from the government of India, they are giving some sort of incentive to the states. So I am also the part of this scheme from the states, So I can say you on the way of authority that we are also on the way of, doing the such things in the state. So this is from my side, and the CEO is very much open to, incorporate your suggestions in their BR's curriculum, as well as the state government of Jharkhand is also very much open to incorporate your ideas. But my suggestion, one thing is that the things which you people are doing should not be the only showcase in the library. That should go to the state government, various stakeholders who are actually implementer of, these things. So I would like to suggest you that with the suggestions you come to the state government, right? A state government as well as urban local bodies. So through, not direct to urban local bodies, through the state government, urban local, and we will organize workshop so that your expert can disseminate the idea in the stakeholders. Thank you. Thank you for inviting me. ये आवाज नहीं आ रही, ध्रुव आवाज ही नहीं आ रही. I'm unable to hear you. I'm unable to hear you.
Okay, yes, we were muted. No, thank you so much, Mr. Gagananji, because I think your suggestions are very valuable, and we will be very happy to engage with you and see that how it is possible to develop the roadmap and engage with you and the Council of Architecture, so that the whole education, the whole curriculum approach that you have in integrating the new and emerging learning from the field, from the practice, and from what we have heard from the new research that is happening on sustainability area with regard to the built environment. I mean, that will be a great opportunity, and we would love to leverage that with you. Thank you very much for this suggestion, and this is very helpful. So what I would like to say, I mean, this has been such a fascinating conversation, and we did not even realize how the time passed, but we were so engrossed in listening to each one of you. It's been a great part of the learning. And to the extent that, we could not even, and we see there are a lot of questions that have come our way, but now I don't think we have that time to take each and every question with the experts, but we would like to tell everyone that the questions that you have sent to us, we will share that with our experts, and we would like to get back to you with their responses and whatever other material that we may have that you may find useful. So I will not even attempt to conclude now, but before we sign off, I would like to ask my colleague Rajneesh that any key major concluding takeaway points that you would like to make.
Thank you, Anumita. I think the one thing which we need to work, like both at city level as well as at the educational level, curricula, in terms of norms and nomenclature and everything, is that somewhere the neighborhood concept and the kind of development or initiative which is required at neighborhood, which is more important, because that's where the layout are losing right now. Because we do have ECBC and we do have bylaws and other things which are there for, you can say, individual buildings as well as to the city and town level. But when it comes to gated community, or largely what is the format of development which we are following right now, so we do not have indirect controls are there, but direct controls are not there. And lacking that, whatever additionality which we created because of energy conservation building code or the kind of strengthening which we do for envelope and all, they get lost moment you put the context into the layout of the site. That's where the challenge comes. Your wind do not penetrate, your structures are placed so closely with each other, there is hardly any visibility of those. So these possibilities is the time where when the concept or the trend is towards the gated community or the way the things are, we need to look at the area as an approach rather than just taking building or city as an approach, because that's the path which now needs to be strengthened both in curricula as well as in the regulations and the nomenclature which we see.
Absolutely, Rajneesh. And what is so clear from all the presentations that we have heard today, that all these new experiments and what we are practicing in a campus, the campus kind of becomes a micro ecosystem where we are demonstrating sustainability in such a holistic and a systemic manner. And this kind of is a proxy for what is possible at a city scale, at a regional scale. So the campuses are actually taking the lead, and that leadership, which is getting defined and with such amazing creativity, imagination, and yet science-based solution and rooted in the local climatic advantages and the local tradition, the traditional architecture that has also evolved within that climatic context. So this kind of integrated way of finding locally appropriate climate solution is going to be the defining paradigm for the future. And that's what we want to see getting scalable. Policies are important to create the mandate for the change, but I think the leadership that we're already demonstrating through practice, that what creates the hope and optimism for all of us. So with that word, thank you so much, all of you. And it has been an amazing conversation. We have learned so much from you, and we promise that we will continue this conversation. This is not in one-off, and we will come back to you and see that what more is possible and how do we really make this a movement in the country. So thank you. Thanks a lot, everyone. Thank you, the great audience we have had. It is an amazing public connect which has been so inspiring for us. So thank you once again. Thank you very much. Thank you, Jyotirmay-ji, Ashok-ji, Vasavanna-ji, Neeraj-ji, and Gajanand-ji, and we are coming back to you again very soon. Thank you, and my colleagues. Thank you. Bye-bye.
Bye.